Okay, in this example, we want to find a least square solution of ax equals to b, where a is given the 3 by 2 matrix and b is given the vector there. Okay. All right. So this, we can tell that this solution, right, is, b is definitely not in the column space of a. Okay, we can verify that because if we can't even try, because we know that a is, it's not a square matrix. Okay, so the only way we can solve this is to do a least square solution. And so in the box here are the normal equations, and those are derived in another video. Okay, so let's go ahead and just find A transpose times A. Okay, so A transpose will give us 4, 0, 0, 2, and then 1, 1. And then we're going to multiply this by 4, 0, 0, 2, 1, 1. Okay, which is A. Okay, so this is going to give us a 2 by 2. Okay, so we're going to get 4 times 4, 16, plus 1, so that gives us 17. And then we have 4 times 0, that's 0 plus 1. And then we're going to get, let's see, 0 plus 2, or plus, I'm sorry, 1. And then 0, 4, and 1. So it's going to give us 5 here. Okay, so now we have to compute A transpose B. So 4, 0, 1, 0, 2, 1. Okay, times B, 2, 0, 1, 1. Okay, so this is going to give us a 2 by 1. So we have 8, so 4 times 2 is 8, plus 11. It's going to give us 19. And then we have 0 plus 0, and then plus 11. Okay. Okay, so now our system, right? Okay, so we have A transpose A, okay, which is here. Okay, and then we have A transpose times B, which is here. Okay, so we have 17, 1, 1, and 5. Times x hat equals to 19, 11. Okay. All right, so we can go ahead and we can solve this by taking the transpose, okay, of this matrix here. Okay, so A transpose A inverse. Okay, so we're going to take the inverse of 17, 1, 1, and 5. Okay, so that's going to be 1 over the determinant of this matrix is 84. Okay, and then we're going to multiply this by the matrix 5, negative 1, and 17. Okay. All right, so we're going to take this and we'll multiply it by our vector 1911. Okay. So x hat will be equal to 1 over 84 times 5, negative 1, 17, and then times this vector. So this is going to give us, okay, the vector 1, 2. Okay. All right, so that is our least squares solution. So now let's calculate the least squares error. Okay. Okay. Okay, so the least squares error is going to be, it's the distance between the vector b and ax hat. So we're going to take the norm, okay, the length of this vector, which is the norm, okay. All right. So if you remember from the previous videos, this is the z component. So this is in the orthogonal complement of the column space of A. Okay. All right. So now, okay. So we have, B was 2011 or 2011. Okay, minus. So A was 400211 times x, which is 12. Okay. All right, so this is going to give us, we have 2011 minus, okay, so we're going to get, let's see, 4, okay, and then 4, and then 3. Okay. All right, so then we have minus 2, negative 4, and let's see, 9. Okay. Oh, sorry, not 9. This is 8. Sorry. Oops. Okay. All right, let's see. Just double check everything here. See if okay. Okay, so now we have the vector, we have the difference of b and ax. So we're just going to take the, all right, we need to calculate the length of that, okay? Okay, so to get the length, you just basically, the length of the vector is just squaring the components. Okay, and then taking the square root. So we're going to have minus 2 squared plus negative 4 squared, okay, plus 8 squared, okay, and then we take the square root. So this is what's called the Euclidean norm, okay. All right, so let's do a calculation here. So we have okay, so yeah, so we get square root of, yeah, so this is going to be 84, and then the square root of that, this is going to be approximately 9 point, let's round it to 2 decimal places, so 9.17. Okay, so that is the least squares error. Okay, that's the minimum. Okay, that's the smallest error we can get because of the orthogonal decomposition theorem. Okay, all right. So